When dealing with gravitational potential energy at great distances, we have to use an equation derived using calculus. And here it is. The gravitational potential energy is equal to the negative of the universal gravitation constant multiplied by the mass of the object. Let's say it's a rocket ship, or let's say a ball that you throw into the air, multiplied by the celestial object of mass m, divided by the center-to-center distance r. So let's say we want to throw an apple into the air with such a speed so that when it leaves your hand, it travels way out into space, and as it travels out there, it's slowing down, and when it comes to rest, the gravitational potential energy is, for all practical purposes, 0. We would then say that the apple we threw has escaped the gravitational pull of the Earth for all practical purposes. So let's see if we can figure out what the escape speed is for an object leaving Earth. Okay, so at the surface of the Earth, it has this gravitational potential energy. And that's equal to negative g times the mass of the object we're throwing times the mass of the Earth divided by the center-to-center distance, which in this case is the radius of the Earth. When the object we threw has escaped, it means that it's at a location where, for all practical purposes, the gravitational potential energy is 0 and its kinetic energy is 0. Now we're looking for the speed at which we have to launch this, which is the escape speed. So we do have another type of energy here, and that's kinetic energy. So the kinetic energy of the rocket or ball or whatever we're launching is equal to 1/2 mv escape speed squared. If we add these two quantities together, we should get 0. You can think of this gravitational potential energy as a binding energy. It's what's keeping it held on Earth. And it's the kinetic energy that we have to give it so that it can escape. So let's write an equation, conservation of mechanical energy. We have 1/2 mv escape squared plus a negative g times me over re. Add those two together and we get 0. So now let's solve for escape speed. Well, first of all, the mass of the object, which in this case was supposed to be an apple, cancels out. So the mass doesn't matter. Remember, there's no thrust here. The thrust is only to get it up to the escape speed. But once it gets up to escape speed, which might be a few miles above the surface of the Earth, the thrust stops. So basically we have a free fall problem here. So that's why I originally said it's like throwing an apple into the air. I mean, as soon as it leaves your hand, it's in free fall. So if we solve this for escape speed, we get the square root of 2g me all over re. Putting in the numbers, we have the gravitation constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. The mass of the Earth, 6 times 10 to the 24th kilograms. And the radius of the Earth, 6.4 times 10 to the 6 meters. Okay, let's see what we get for the escape speed. And I'm getting 11,000 meters per second, or 11 kilometers per second. So that's the escape speed from the Earth. Now suppose we want to go beyond that, well then we would just have to increase the speed at which we launch the rocket.